Hello, good morning.
Morning, sir.
Good morning. Okay. Yeah. Previous class we solved few examples on the binary search tree and the traversal. So now, today we'll discuss how to delete from the binary tree, delete an element from the binary tree, which we haven't discussed till now. Even the deleting part was not there in the lab program also. Lab program is only for constructing the binary search tree and traversing it in all the three techniques, and also searching a given node in the tree, searching for a given key in the tree. Now, how do we perform the delete operation from the binary tree? So, previous classes for the other linear data structures like list, circular singly linked list, doubly linked list, okay, you understood how to perform the delete operation at various positions. Now, similarly, how do we perform the delete operation in case of the non-linear data structures such as binary trees? Now, so there are three cases which are possible for deletion in case of the nonlinear data structure such as trees. One is this one, deletion of the leaf node. So you can do that. Deletion of having node, deletion of node having only one child. So deletion of node having two children. Okay. Now these are the three possible cases where you can go for deleting a node. Deletion of a leaf node, deletion of a node having one child, deletion of a node having two children. Okay. So now we'll just have a look how to perform the deletion of a leaf node. Okay. Now this is an example sample tree which is taken here, and you know these are the leaf nodes. Okay. So this is the simplest deletion among the other two. So deletion of a leaf node is the simplest deletion when compared to deleting a node having one child and deleting a node having two children. Okay. Now, from the above tree, if you want to delete the node having the value 6, okay, this node, so then we will have to set the left pointer of its parent node. So that is 8. So 8 will be having the left pointer and the right pointer. So if I am interested in deleting 6, then I should be making the left pointer of node 8 as the null. So the left pointer of the node having value 8 is set to null. Now if I do that, so then the leaf node is deleted. So this is what you are seeing, the status before deletion, and this is the status what you are seeing after deletion. Now 6 is deleted, and to the left link of the node 8 we are storing the null. So hence we say this is the simplest form of deletion from the tree. Okay, deleting any leaf node is very simple. Say for example, I want to delete node 7, which is the right child of node 8. Now what is that I need to do? I have to go for making the right link of node 8 as null. Or make it as null and go for freeing this. Okay, this is how you can go for deleting. Okay, so how to do it programmatically we will see soon. This is deleting the leaf node, which is considered as the most simplest form of deletion when compared to the other two. So deletion of a node having one child. Now if a node has got one child, how do we delete it? Okay. Now for this, I have the tree here. You can just observe this tree. Now here 15 has one child, that is 18. Now if I want to delete this, how can I go for deleting? Now this if I delete, so 15 if I delete, so this will become something like a skewed tree. Okay. It becomes like a skewed tree. So ನಾನು ಇಲ್ಲಿ ಮಾಡಬೇಕಾ ಬೇಡವಾ ಹೇಳ್ಬಿಡಿ ಸರ್. ನಾನು ಸರ್ ರೆಕಾರ್ಡ್ ಮಾಡ್ಕೋತೀನಿ, ನಾನು ಅದನ್ನು ಯೂಟ್ಯೂಬ್ಗೆ ಹಾಕ್ತೀನಿ, ಇಲ್ಲಿ ಏನೇ ಡಿಸ್ಟರ್ಬ್ ಆದರೂ ಅದು ರೆಕಾರ್ಡ್ ಆಗುತ್ತೆ. ಇಲ್ಲ ಇಲ್ಲಿ ಮಾಡಬೇಡಿ ಸರ್ ಅಂದ್ಬಿಟ್ರೆ ನಾನು ಬರೋದೇ ಇಲ್ಲ. ಇಲ್ಲ ಹೇಳ್ತೀನಿ ಸರ್. Sorry. Now if I want to delete this 15, then this become a skewed tree. That means it gets separated from the original tree. Okay. Now so when I am deleting a node with one child, I have to take lot of care. Okay. Now after deleting this skewed tree, which becomes a skewed tree as or an independent tree, should be linked with the original tree. Now how do we do that? Say if you want to delete the node 15, here I am interested in deleting 15. Okay, then we simply copy node 18 at place of 15. So node 18 we go to copy to the place of 15 and then set the node free. After copying this node 18 to this position, I should go for freeing the node 15. So in order successor. Now how to do that? Now why 18 should be copied to this place? So it was in order successor is always copied at the position of the node being deleted. Now if I write the in order traversal of this tree, so what I'll do is I get 18 as the in order successor for 15. Always. So the node which you are trying to delete, its in order successor should be made into the position of the node that is being deleted. OP people are following?
Yes, sir.
Now before deleting any node which is having one child, okay, what you got to do is you got to traverse the tree, get the in order traversal of the tree. After getting the in order traversal of the tree, just see which is the immediate successor of the node which you are trying to delete. Now if I write the in order traversal for this tree, I get 18 as the immediate successor for the node 15. For node 15 I get 18 as the immediate successor, and now I should go for making this 18 to the position of 15 and free this. Okay. So that is how we go for deleting a node with a single child. So by making its in order successor, immediate in order successor into the place of the node that is being deleted. Now once I go for deleting, so this is how it looks. You can see here. So 15 is deleted. Now this 18 takes the position of 15, and this is how your new tree looks like. So this is the status what you are seeing after deletion. Is that clear?
Yes, sir.
Yeah. Earlier, see 20 was the grandparent of 18. Now once you delete this 15, this 18 is it becomes the left child for the node 20. Okay. Next. Now that was the second case where you delete a node having only one child. Okay. And next, similarly, a node can also have two children in binary tree. Okay. Since we are discussing this for the binary trees, in binary tree you can have a node can have maximum how many child nodes? Only two child nodes. Okay, not more than that. Hence it is called as what? The binary tree. Now the other case, the third possible case is node having two children. Now say again what I am considering here is I want to delete the node 7. So this is what I want to delete. Now how do I once I delete this, so this will become a skewed tree. So see, if this is deleted, you get three trees. This original is one, this is another one, and this is another one. It becomes a form of a skewed tree, and this should not happen when you are deleting. Okay. Now how to do that? Okay. Let us consider that we want to delete a node having the value 7. This is what we want to delete. So we will then find out the in order successor of 7. Now you got to write the again in order traversal of this tree. Okay. And then just find out the immediate in order successor of 7. The in order successor will be simply copied at the location of node 7. So whichever node is the in order successor, it will be copied to the position of 7. So that means copy 8 at the position. So if I am writing the inner traversal for this tree, okay, I'll be getting 8 as the immediate successor for 7. Now that means 8 should be copied to this position. Okay, so means copy 8 at the position where the value of the node is 7. Set the left pointer of 9 as null. Okay, because after I copy this to this position, so 9 will not have any child node. I have to make the left pointer of 9 as null, and this completes the delete procedure. Okay, so just I'm going for copying this 8 in the place of what 7. So by doing this, so I can go for deletion of a node which is having the 2 children. So deletion here is nothing but copying this 8 to the info field of the node 7. Okay, so copy this, and you don't have to change the left link also and right link also. They remain same. Only thing what you are doing is replacing the value 7 by 8, and since you are replacing the value 7 by 8, so now this left link of the node 7, so node 9 must be made as null pointer. So is that clear?
Yes, sir.
Okay, so writing in order traversal, writing in order traversal is, hello, tell me.
Sir, in case 2, after 15, 16 should be the in order successor, sir.
Which one? For case 2, case 2.
16 should be the in order successor, no, sir.
16, have you people written? Try to write the in order traversal for this, and just tell me the in order traversal for this.
I'm not done.
Okay, do it, please. Start writing the in order traversal for this tree. Can one of you write and tell me the in order traversal for this tree? So I think I got the response here in the chat box. Okay, so it is, I don't know, 6, 8, 10, 15, 16, 8, no, not this one. So after for 15 you are getting it as 16, huh? Okay, so in order successor of 15 is 16. Okay, in order successor. Okay, check it again. Is this correct? Sorry, this one, is it 16 or 18 after 15? Hello? Waiting for your response, please. Uh, 16 you're getting. Okay, so anybody else did it? Okay, 16 sir. Okay, so if the in order successor is always copied at the position of the node being deleted for in order successor for this 15 is 16. Okay, I think we have made a mistake here. So if it is not 18, sorry, if it is 16, now what we do now, we take this 16 and we overwrite it by overwrite this 15 by 16, and this remains same. Okay, so please do make a correction. Okay, here there is a mistake, I think. So in order successor for 15 is 16. Now what we do, we take this and we overwrite it. Is that clear?
Yes.
Now similarly here also. Now whether the case 3 is correct? So for 7, what is the in order successor? Is it 8? Right for this also? Okay, 4, 6, 7, 8, and it is 9. Oh, for 7 what it is? So for 7 it is 8. Okay, for 7 here it is correct. Case 3 is correct, but case 2, I think there is a mistake. So 18 is not the immediate successor of the node 15, it is the 16. Now what you should do now, you should go for replacing this 15 by 16. Okay, if there is only one child node for the node which you are trying to delete, so just find out the immediate successor and replace it with the node which you want to delete. So that's all, and you don't have to change any of the pointer. So case 3, again you find out the immediate successor since it has got 2 childs. Okay, so now the immediate successor is 7. Replace this, 8. Replace this 7 by 8 and go for setting the left link of the node 9 as null. So those are that is the changes what you got to do. Now after that, this is how the tree new tree looks like. Okay, next. Okay, and there is the implementation also for this. Okay, so delete node root I'm passing, and then key I'm passing. Here I search for this. See, using this function search, I find the key, because for deleting I need to identify some element, right? So I'm searching. Now my key is now the item to be deleted. Okay, now so and once it finds, temp will be pointing to that. OP people are following? So I'm not elaborating on the search method. Now if you pass the root key and all these things, now what search method returns you is the pointer to the element which you want to delete. OP people are following?
Yes, sir.
Now it's written also here. Temp is the node which is to be deleted, and parent is the node which keeps track of the parent node of temp and the temp successor. Parent is a node which keep track of parent of node temp. So parent pointer, it points to the parent of what? The temporary node, the node which you want to delete. And temp successor is for keeping track of the successor of the temp. Okay, so 3 things we have. So temp is pointing to the node which you want to delete, and parent is pointing to the parent of the temp node, and temp successor is pointing to the what? Immediate successor of the node to be deleted, something like this. Here if I go, now this is the node which I want to delete. Okay, who will be pointing to this? So I have temp pointing to this, and who is pointing to its parent? So I have parent. So the name of the pointer is parent is pointing to this, and root is pointing to this. Root is pointing to this, and the temp successor points to the successor, immediate successor of the node to be deleted. So temp successor is pointing to this, temp underscore succ. Hope you understood? Okay. So when you pass, one second, yeah. OP people can see my screen. Is it refreshed for you people? Okay. See, when you pass root key and parent, okay. So what happens is, so the temp, this will find out the key which you are looking for, and it will return the address of that node. Okay. Next, deleting a node with 2 children. So let us assume the third case. We are taking the third case now. So deleting a node, we are assuming the node which I want to delete has 2 children. Now what I am doing now? So if temp arrow left not equal to null and temp arrow right not equal to null, what does it mean? So the node which I am trying to delete has how many nodes? 2 child nodes, or 2 children it has. Okay. Now this is the case. This condition is checking whether the node has 2 children or not. So now if this condition is true, so the node has got 2 children. Now you have to go for deleting as per the case 3. Now what we are doing, so parent is equal to temp. Okay. So that means parent also points to the node temp, and temp successor is equal to temp arrow right. Okay. So temp successor is made to point to the right child of the temp node, and then so while temp arrow successor successor arrow left not equal to null, what we do, so parent is equal to temp successor, and then temp successor is equal to temp successor arrow left. Okay. So we keep doing this until the temp successor arrow left not equal to null. So once this condition is false, what we do, we come out and we are going to replace the temp data. So so the info field or the data field of the temporary node which I want to delete, with the data of the successor node. Okay. So that is what temp arrow data is equal to temp arrow successor data, and then make parent arrow right is equal to null. Okay. Parent arrow right is equal to null you make, and then say now node is deleted. Actually we are not freeing the node. What we are doing is just making the null pointer. We are overwriting the temporary node with the data field from the temporary successor node. Okay. So and finally we make the parent arrow right field as null, and we say now it is deleted. And similarly, so deleting a node having 1 child. Okay. So again, how to check that? So temp arrow left not equal to null and temp arrow right not equal to null. Okay. Yeah, sorry. This is equal to. So 1 child, how to check? Temp arrow left not equal to null. That means it has the left child. And similarly, temp arrow right equal to null. So there is only 1 child present. What child it is? The left child. Now what we do? Temp arrow left is equal to temp. Okay. Parent arrow left is equal to temp. Parent is pointing to the next node after the temp, and parent arrow left is equal to temp arrow left. Else parent arrow right, if this is not true, okay, parent arrow right is equal to temp arrow left. Okay. So you people can imagine mentally all these things, and then make temp as null and free temp. So here we are freeing it. Okay. Next, so right child. So this is for 1 child again. For the case left child, if there is a left child, only 1 left child present, and this is similarly for the right child. When I say case 2, either it can be the left child or it can be the right child, and this part is for the left child and this part is for the right child. Okay. And from here this all together, So from here it is for what, one child condition. Okay, again what we do now, so if left temp arrow left equal to null and temp arrow right not equal to null, that means it has one right child. Now parent arrow left is equal to temp, so we say parent arrow left arrow temp arrow right. Okay, so we are making the temporary right field assigned to left field of the parent node, else we make parent arrow right is equal to temp arrow right and make temp is equal to null and free, and we say node deleted. So this is how we go for deleting a node with two child and a node with one child. So for the left child, and here it is for the and here it is for the right child. Now similarly, if the node has no child, if the node which you are trying to delete is the leaf child, okay, it's easy as I already told you. So temp arrow left is equal to null and temp arrow right is equal to null. If both are equal to null, it is the leaf node. So then you make parent arrow left is equal to, if parent arrow left is equal to temp, make the left field of the parent as null, else make the right field of the parent as null. Okay, and then you say deleted. Now here you are basically checking whether the leaf node belongs to the leaf node, whether the leaf node is the left child or the right child of the parent node. So if it is a left child, we make parent arrow left is equal to null. If the leaf node is the right child, then we make parent arrow right is equal to null. Hope you understood till here. You are performing the delete operation for all the three cases. Okay. So now we'll come here. So I'll be sharing all these PDFs to you people. So now threaded binary tree. So threaded binary tree. Okay. So when we are writing a tree, binary tree, so you can have the null pointers also. Okay. So too many null pointers. So too many null pointers, what it is doing, it is consuming the memory, and it doesn't look good. Now what binary thread does is, it will go for converting those null pointers into a kind of thread. Okay, so here is the simple analogy. See, so if I say I have n nodes, okay, and the number of non-null links is n minus 1. Okay, so this is the total number of nodes, and n minus 1 non-null links I have, that means the links which are not null, and say total number of links are 2n. Then how many null links will be there? So the number of null links is total number of links minus total number of non-null links. Okay, so that is, so there will be n plus 1, okay, maximum n plus 1 what it is, null links. Okay, now if you go for replacing all these null links or the null pointer some useful threads, so we call it as a threaded binary tree. So where we go for converting all this null pointers, or null links into an useful thread is called a threaded binary tree. Okay, so because normally when you are writing tree, in the previous example also if I take, so there will be many nulls. So if, say for example, there is a node and it doesn't have the left child, so usually what it will have? Usually it will have a null pointer there. And similarly, one more node if I take, if it doesn't have the left child also and right child also, both its left link and right link will be stored with the null pointers. Now these things I need to avoid. How to avoid these things? By converting it into a form of threaded binary tree. Now we'll see how to do that. Okay. So pointer arrow left child is null. What does it mean? That means the corresponding node doesn't have the left child, hence its left field or the left link is stored with the value null. Right now, so I don't want it to be stored as a null pointer. I need to go for converting this into a thread in order to make the threaded binary tree. Okay. So how to convert it into a thread? So replace it with a pointer to the node that would be visited before PTR in an in-order traversal. So first thing, when you want to convert any tree into a threaded binary tree is, you should go for writing the in-order traversal of the tree. And if you want to convert the pointer, the left pointer which is holding the null value into a thread, you should go for replacing that with the pointer replacing it with the node which is before the in-order traversal of that particular pointer. And similarly, if you want to convert the null link of the right child, okay, to a thread, you should go for replacing the pointer with the node that would be visited after the pointer in the in-order traversal. Okay, so by doing this, you can go for converting a binary tree with too many null links into a threaded binary tree. Hope you understood. Okay, so first write the in-order traversal. So when you want to convert the null pointer of a left child, okay, so you should go for replacing that with the node that would be visited before the pointer in an in-order traversal. And similarly, when you want to convert the null pointer of a right child, so you should go for replacing that with the node that would be visited after the pointer in the in-order traversal. So I have the example here, I'll show you. So this is a threaded binary tree. So before converting it into threaded binary tree, it was just a normal binary tree, and for that normal binary tree, so in-order traversal is already written here. Okay, H D I B E A F C G. This is the in-order traversal of this tree. Now let us start from here, from the root node. Root node is A, and it has already got two child nodes. Since it's a binary tree, so it has both the childs, left child as well as right child, and hence the left link of the node A is pointing to B and the right link of node A is pointing to C. And there is no question of what null links are for the node A. Okay, so and it is not necessary for you to create a thread also. Now let me walk the left subtree of the node A. When I walk through the left subtree of the node A, I reach B. Again here in B I check whether the left link of B or the right link of the B is null. So when I check the left link of B, it is not null because it is pointing to D, and when I similarly check for the right link of B, it is also not null because it is pointing to E. Correct? So there is no need for me to create a thread for the node B. Now again, let me keep traversing it along the left subtree of B. So when I keep traversing, I reach the node D. Now when I reach D also, again I go for checking the left link and the right link of the D. So both are not null. So they are non-null pointer because they are pointing to H, and so left link of D is pointing to H, and similarly the right link of D is pointing to I. And there is no scope for you to add a thread to the node D also. And let me continue my walk towards the left subtree of D. Now I reach H. When I reach H and examine the left link of H and the right link of H, they are null pointers because this is the leaf node and it doesn't have the left child or the right child. Hence the left link and the right link of the node H are right now null pointers. So what threaded binary tree says, whenever there is a null pointer, convert that into a thread. Okay, observe here. Now I take H now. Now as per the definition, okay, if PTR arrow left is null, you should be replacing that with the node that you are going to visit before the pointer in the in-order traversal. Okay, so this is what the node is right now, H. So its left link is null. Now left link, I am saying you should go for replacing, okay, the null pointer with the pointer to the node that would be visited before the PTR. So H, and for H there is no node here. Getting? So before, this is the in-order traversal. For the in the in-order traversal there is no before node for H, hence I am saying it as dangling. Okay, and similarly I check whether the right link of the node H is null. Okay, so right link of the node H is also null. Now I'll go for checking whether there is a node which is very next to the node H. So the immediate successor for node H is D. That means instead of making the right link of H as null, I should create a pointer which points to the node D. So same thing is done here. In the right link of the node H, I have the address of the node D, okay, which is an immediate successor in the in-order traversal of this particular tree for H. So it is pointing here. OP people understood? So there is no left node for this, but there is a right node for this in the in-order traversal. Okay, in the right link of H, I should be going for writing the pointer of D. Okay, so it's pointing here. Similarly, I backtrack, come to the root node of H, and then I come to I, okay, which is the right child of D. Now I go for checking whether there is the left link of I is null or not. Yes, again the left link of I is null. Now I should be converting that into what? Thread. Now how to convert? I'll look into my in-order traversal and I'll check whether there is a node before I. Yes. What is that? D. Now in the left link of I just store the pointer to D. So this is just the pointer that is established. And similarly, a right link of I am checking. Yeah, right link was also null. Now I have to I just look what's there after I in the in-order traversal. In the in-order traversal, after I have B. That means instead of storing null, I should be storing the pointer to B. So pointer to B is stored and it is pointing to this. Okay. Now again I backtrack, I come to node B. So when I look for the right child of node B, yes, right child for node B exists and it is E. Okay. And he also, this is the leaf node again, the left link is also null and right link is also null. And by looking into the in-order traversal, so in order before node of E in the in-order traversal is B, so the left link which was null now, so pointing to, we make it to point to the B. So these are all the threads what we are creating. This is a thread, this is a thread, so this is a thread, okay, and this is a thread. And since the right link is also null, so again I see what is the node that is after E in the in-order traversal, it is A. So from the right link of E, we can get back to what? The root node A. So this is the thread created from E to A. And similarly for all others. And for G, if you look in, okay, after G there is no node. Okay, before G there is a node in the in-order traversal, that is C. Now it is pointing here. After G there is no node, so it is a dangling. Understood how to construct the threaded binary tree? Okay. Now before writing the threaded binary tree, so you got to take the original binary tree, and to that binary tree you have to write the in-order traversal for that binary tree, and then you should go for converting the threaded binary tree. Now I'll give you an example, so please try to do it. So I think the previous class I gave you 3 examples, yes or no? 2 to 3 examples I gave you, and you people have already solved it. So take all the 3 examples, and in-order traversal also you have already written. Just convert that into each of them into a threaded binary tree. Start doing it. So I'll take 1 second. I'll take a blank slide. Okay. Can anyone so tell me the in-order traversal of the first tree that we considered as an example in the previous class? Just tell me the in-order traversal. Hello? Able to hear me? Yeah, tell me the in-order traversal for the first tree that we solved in the previous class. Have you people written it? One of you can unmute and tell me, because I want to write here. Okay, it's there in the chat. Okay. This one 0, 1, 2, 3, 4, 5, 6, 7, 8. Is it the one? Yes or no? Hello? Okay. Okay, this one. And can you just tell me the corresponding tree? I'll write it. Tree for this. This is the in-order traversal. This is the in-order traversal. Just tell me the tree for this. No, not for this. The original tree. The original tree out of which you wrote this in-order traversal. Please. Because I don't have that with me now. So if one of you unmute and read out, I'll write it. 5 is the root node. Thank you. Okay. 2. Okay. 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 That's all. 7 is there, still 7 and 8. Okay. Right child is 4. Okay. Done. Okay. Uh, 7 and 8. Hello? 5, 6. Right child is 8. Okay. For 8 left is 7. 7. Okay. Yeah. Now for this you go for writing the threaded binary tree. So in-order traversal is already here. Let me start from here. 5. Okay. So it has 2 childs. Both are non-null links. Okay. So here also 2 also has 2 childs. Both are non-null. So when I take 1, okay, as the left child, but there is no right child. Okay, that means the right link of 1 is null. Okay. Now what I have to do now? So I have to see what comes after the node 1 in my in-order traversal. After 1 it is 2. That means I have a thread created from here to here. Okay, next I take 0. So left link is also null, right link is also null. So what is there before 0? Okay, before 0 there is nothing. So this is dangling pointer. And after 0 there is 1. Then instead of making the right link of 0 as null, I make it to hold the address of 1. Why 1 only? Because the successor of 0 in an order traversal is 1. For the right link successor, for the left link its previous node. And next, if I take 3 again, there is right child, but there is no left child. So for 3 again, see its previous node is 2. Now from here a thread to the node 2, and then 6 also. Sorry, let me complete with the node 4. Node 4 also doesn't have the left and the right child. So 4 previous is 3, and 4 next is 5. Okay. Now from here a thread to the root node 5, and 6 if I take, there is right subtree but there is no left subtree. From 6 it should go back to 5. And then 7 there is left subtree but there is no right subtree. Right field of 8 is null. Okay. Now for 8, see after 8 there is nothing. Okay. So now again it becomes a dangling. Any binary tree you take, there will be 2 dangling pointers. Okay. Next 7 if I take, okay, so left is also not there, right is also not there. 7 left I have 6, it goes to 6, and 7 right is 8. Hope you understood. This is what the threaded binary tree. Okay. And similarly, so try to write it for the other 2 as well. So because the previous class I hope we solved around 3 examples. So this is what I have written for the first example. So similarly do it for the second and third also. Just write it in a piece of paper and post it in the chat box. See, in-order traversal is used while deleting from the tree, and in-order traversal is also used while constructing the threaded binary tree. Remember this. Yeah, start doing for the other 2 examples. Start construct the threaded binary tree for the other 2 examples, and write it in a piece of paper and post it in the chat box. So just do that. Meantime, I'll finish taking the attendance. Okay, I think there is no internet. Okay, I think the server might have disconnected from the internet. Look into that. I'll download the attendance list. So those who have finished doing it, please post it in the chat box. Who has finished? Anybody finished? Okay, I have downloaded the attendance list. So solve those two problems also, and at least share me in the tomorrow's class. Okay, any doubts?